Νομίζω ότι είμαστε έτοιμοι να προχωρήσουμε στο επόμενο session του συνεδρίου. Επιτρέψτε μου μία εισαγωγή στα ελληνικά. Βρισκόμαστε στο πρώτο επιστημονικό συνέδριο της μονάδας μας, της μονάδας Υγεία Εμβριογένεσης. Νομίζω ότι τα αποτελέσματα του συνεδρίου τις πρώτες 2 μέρες έχουν ξεπεράσει τις προσδοκίες μας και το μεγάλο ευχαριστώ ανήκει καταρχάς στον αγαπητό φίλο, τον καθηγητή, τον κύριο Μακράκη, αλλά και στον κύριο Σφοντούρη, τον Διευθυντή του Εμβριολογικού Εργαστηρίου και το Επιστημονικό Συμβούλιο της Μονάδας για την εξαιρετική δουλειά που έκαναν οργανώνοντας το συνέδριο αυτό. Έχουμε την τιμή να έχουμε μαζί μας τον αγαπητό φίλο και δάσκαλο κύριο Ματζαβίνο, τον οποίο εκτιμώ απεριόριστα, επιστημονικό υπεύθυνο της Μονάδας Institute of Life Ιασό και πρόεδρο της ΕΛΕΙΕΑ. Το συνέδριο συνεχίζεται με ένα session, μια εικόνα από το μέλλον, που αφορά την εφαρμογή της τεχνητής νοημοσύνης στην υποβοηθούμενη αναπαραγωγή. Εδώ και 1 χρόνο έχουμε την τιμή να έχουμε μια εξαιρετική συνεργασία με τους αγαπητούς φίλους Ντανιέλα Γκιλμπόα και Ντάνιελ Ζάιντμαν, οι οποίοι θα μας παρουσιάσουν το πώς η τεχνητή νοημοσύνη εφαρμόζεται στην υποβοηθούμενη αναπαραγωγή μέσα από την δουλειά της AIVF. Και στην συνέχεια θα περάσω το μικρόφωνο στον Γιάννη τον Σφοντούρη, ο οποίος θα κάνει το introduction της πρώτης ομιλήτριας. Γιάννη, ο λόγος σε σένα.
Good evening, everybody. I'm going to switch to English for obvious reasons. So it is my great pleasure to welcome and introduce Daniela Gilboa. Daniela is a colleague. She's an embryologist, so she knows the hard work that goes inside the lab. She knows about the dilemmas and the difficult decisions that embryologists have to make every day. But she's also a visionary and a pioneer because she realized that the application of AI in IVF can have a place. So she's the CEO and co-founder of AIVF, which is a technology, artificial intelligence company based in Israel that develops solutions for AI assessment of embryos. So she's the best person to talk to us about development of artificial intelligence solutions for the evaluation of human embryos. Daniela, welcome, and the floor is yours. Mind the step.
Thank you so much for the kind invitation. I'm very honored to be here and present AIVF. Okay. We're actually working with Higia and the amazing IVF team here for about a year now, and we're about to expand our collaboration. So what I'm going to talk to you about today is I'll take you to the more AI side, less IVF, more AI, and I will explain how we developed an AI model that's explainable or can actually shows us clinicians or embryologists what the AI is looking at while it's evaluating embryos. So again, I'm the co-founder and CEO of AIVF. So this is, I tried to map the IVF process, but in a different way. I think we can see the IVF process as a series of decision-making or decision-making points, and we can optimize each and every point with an AI application. And of course, we're going to be focusing on the embryo evaluation as we think this is the most crucial part of the IVF process. And if we look from the computer science side or computational embryology or computational medicine, most AI models developed were around the imaging or bioimaging field, again, because our ability to develop AI models that can help us diagnose or make better treatment decisions is becoming enormous. And as you can see, most of the applications are around biomedical imaging. So as we all know, the million-dollar question in IVF is which one? Which embryo will give us the baby? We don't really have an answer as embryologists. We have what I love to say, kind of like a guesstimation, right? It's a very soft way of evaluating embryos, a very subjective human analysis kind of process. So what I'll be explaining today, or talking today, is about this. I know it looks Chinese, so we'll take each and every term here and translate it into clinical meaning. So what you can see, what you'll understand is the beauty of such applications and how it really, really changes medicine or IVF. This was done in collaboration with a leading university in Israel, Ben Gurion University. We had a PhD student, and these are one of the, I would say, examples of how collaborating with AIVF can bring. We have many many PhD students and master's degree that have been studying AI applications in IVF. So why do we need at all explainable AI in medicine, mostly? And so part of what we want to understand is why not rely on the off-the-shelf models that we have now, and why do we need to put such energy into the next phase or the next stage of AI models or AI development, and these are explainable AI. So for us, basically, it's understanding the black box. One of the big questions in AI field today is how do we deal with the black box, or in our case, how can we know that what the AI is looking for is exactly what us human experts are looking at? So this is the reason, mostly about transparency and reliability, that we now develop, and we, as I say, the ecosystem of AI, looking at explainable or explainability of AI developments. So the human-based embryology, I think you all know, is pretty much based on annotating or analyzing 5 or 6 days of a series of images or videos of embryos, and at the end of the day, we get a score or a grading system that is based on known features that we can detect, right? So we can detect the ICM, we can detect the trophectoderm, we can understand the size. We can't really model the ICM or the trophectoderm, but we have some kind of high-level evaluation of what it means. But the question is, maybe there's other features that we cannot see or we cannot detect that are maybe more relevant to the outcome. That's a valid question, and this is what we wanted to see, if we can develop an AI model that not only understands what it sees, but also maybe can find new features, new biological features that might have correlation to the outcome. So what you see here is pretty much this is like a high-level graph of how off-the-shelf model look like. It's a very simple classifier. We usually, on the one side, push inside the data, that's the images or the videos, and the other side, the outcome that it needs to predict. It could be grading, it could be implantation, and we have some kind of probability. We usually talk about being as good as the embryologist, or maybe slightly better than. That's most of the AI models. This is how it looks like, and it cannot really tell us what it's looking at. These are the black box models. But what is interpretability or explainability, or why do we need it? Again, for us to trust, to understand that A, the system or the model looks at the things we're looking at, and B, transparency, making sure there's no bias, and of course relying on the diagnosis. So this is XAI, explainable AI. So this is where I go a bit deeper into the AI world. So usually for us, what we call a sanity check, for us to make sure that the model is looking at what we want to be, what we want it to look at, we usually use heat maps. So what you can see here, I'll talk about the limitations in a minute, but this is what we call a sanity check. There's two different models here. One gave a high score, the other gave a low score, and the heat map shows us a very high level that it detected the trophectoderm, the ICM, or the features that we wanted it to look at. But it has limitations. And these limitations are what you see below. I'll explain. So for us to understand why this is not good enough and what can we make to produce a better model, an explainable model, I'd like to go through two basic terms in AI. So for us to understand how we actually constructed the model. So the first one is entanglement. What is entanglement? Entanglement means, the system or the model usually, when it detects a feature, so the feature may be built from a few sub-features. Okay, so it cannot be separated. I'll give you an example. Going back here, we are not sure whether the model looks at a biological feature, for example, the trophectoderm, or it also has inside some environmental features like the focus or like the type of camera that we used. This is, sorry. So as I said here, the AI might associate embryo quality not just based on the biological feature, but also with environmental features like lightening or color or tone or something inside the image. So for us to disentangle the different features, we have to build a model that actually takes each of these features and breaks it into pieces, okay? Into pieces that can differentiate the biological features and the rest. This is disentanglement, okay? So taking a feature and making sure that we can break it down into its building blocks of biological building blocks and the rest. This is disentanglement. The other term that I'd like to explain is counterfactual explanation. This is meaning like a what if. Imagine that we had like a volume button, and we can play with each feature, like make it stronger or lighter or bigger or smaller, like a volume button. This is counterfactual explanation. So imagine we had a way to build or generate synthetic embryos where we know what this embryo is built from, what are the biological building blocks, and within each building block, we can play with its, with how it's performed or how it's, with its, you understand, okay? So these are the two terms. Disentanglement, breaking down into biological pieces, and counterfactual explanation, playing with each biological feature to understand how it affects the outcome. So this is what we did. And now I'll show you an intuitive explanation before going deeper into IVF. OK. So let's start with, let's take a simple model, and we'll ask it to detect or differentiate between a mouse and a cat. OK? So let me go back. So the first simple model is, it looks simple, but the problem is, as I said before, it's entangled. So all the features are kind of like mixed together. So we have to break them down into the biological pieces, into the ears, the eyes, and the nose. And then there are features which we cannot really separate, like color and size. So how do we understand where the model is looking at? We pull together the counterfactual explanation, and we play with it. So we're asking the model to take the ears and play with the color of the ears and the size of the ears. So all together, we have the biological features and the fact that we can play with it gives us Discover. Discover is our model that is disentangled, counterfactual visual interpreter. This is the Discover model that basically what it does, and this is the beauty of it, and this is the groundbreaking understanding of what we did. This is taking an image, breaking it down into biological pieces, and generating synthetic embryo so we can take each and every biological feature and understand how this correlates with the outcome. This way we can know the question that all embryologists ask, which one is it the trophectoderm that affects the outcome or the ICM, for example? So this model answers it. This is how it looks like under the hood. But what it gives us at the end of the day is a higher performance. So if we took the very basic off-the-shelf models that gives us prediction of about 65, 68, 70%, our model can make it into 80% and even more. This is groundbreaking, and this is the future of IVF. And now, the next thing was for us to take the human expertise and do a sanity check or validate it against an embryologist or a group of embryologists. So we wanted to know whether what the Discover, the model looks at, whether there's an agreement with the human expert. So we checked it, and this is an example on the size and on the trophectoderm. And you can see here, what I show here is this is the counterfactual explanation or the volume button that plays with the size and with the trophectoderm. And what we're showing that each building blocks or each biological feature, we can now know how it affects the outcome. Okay, you understand? It's not a high-level embryo quality that we give a score to the quality or the embryo itself, but here we can actually take the building blocks and understand how each one of them affects the outcome. So once we validated this against the human expert, we then took it to another level and we asked, can we detect new features? Something that the human eye cannot see, or maybe we see, but we can't really model. And so we now have 12 new features that the model has discovered. One of them is blastocell density. So we all know there's some kind of correlation. We can't really model it, but this model can. And again, we check ourselves again and again and again through heat maps and human experts. And this takes us into from a discrete way of, or discrete grading into continuous grading. And why do we need continuous grading? Because we can actually give probabilities of success to each and every embryo. And this is important. So it's not high level 4AA or good versus bad. Now we can actually say this embryo has a 78% chances of implantation, and this is why it has a 78% implantation, because the trophectoderm, because blastocell density, et cetera, et cetera. So the next stage for us was, we called it global validation. And this is how it looks like. I'll take you step by step. So we started with training a classifier, an off-the-shelf model, just to give us the range or a benchmark. So we used about 200,000 images of embryos from different IVF clinics pretty much worldwide. And we established this was a reference model to our Discover model. The second step was training the Discover, training our model, Discover model. And here we used data from 5 independent clinics. And we had an internal validation that showed above 90% generalization accuracy across the sites. The second step was global interpretability. As I said before, we always do a sanity check against the human expert. And we've shown, compared to embryologists, we've shown 95% alignment. And the last step was to put it inside clinics. This is real-world data. And to test the predictions, the accuracy or the performance of the model. And we've shown the implantation, predicting implantation, 88% accuracy, predicting blastulation, 93% accuracy, and cross-clinic concordance was above 90%. These are exceptional results. So this is it. This is the Discover model, and I think it stands a new generation of AI models, and I think the day will come where clinics, IVF clinics, would ask for these kinds of models. I think we can't really go back to working with high-level, good quality versus bad quality. Once we have this that can actually show us what the model is looking at and what really means what is a good embryo versus a bad embryo, these models are really the next wave of IVF. And this brings me actually to the next presentation about how we can take these models and predict not only implantation, but also aneuploidy, and present to the world a test, a non-invasive way of screening aneuploidy. Thank you.
We're going to wrap up the questions and comments at the end of the next talk.